Okay, when merging two trees, we're going to hang a shorter one under the root of a taller one. This means that when merging two trees, we need a way to quickly find the height of both trees. Instead of just computing them, we're going to keep the height of each possible subtree in our forest in a separate array called rank. Namely, rank of I is equal to the height of the subtree rooted at I. Okay? The reason we call it rank will become clear a little bit later. Let me also mention that this way of merging two trees based on their heights is called the union by rank heuristic. To keep the rank, we need a small addition to our make set implementation. Namely, when creating a singleton set, we also set rank of I to be equal to 0. This reflects the fact that it is currently just a root containing one node, just a tree containing one node, that is a tree of height 0. We do not need to change find. So the find operation doesn't need to change rank, and it also doesn't use rank in any way. To merge two trees containing the given two elements I and j, we do the following. We first find the roots of the corresponding two trees by calling the find operation 2 times. We store these roots in variables iid and jid. We then check whether iid is equal to jid. If they are equal, this means that elements I and j already lie in the same set. So we just return in this case. So this is done in the following if loop. We then check whether the height of the tree containing element I is larger than the height of the tree containing element j. If it is larger, then we hang the tree with the root jid under the root of element iid. This is done as follows. Parent of jid is set to iid. Otherwise, we do the opposite thing. We just assign parent of iid to be equal to jid. The last thing is that we need to check whether the height of the corresponding two trees are just equal. Let me illustrate this again with a small example. Assume that we are merging the following two trees. In this case, the heights of these two elements and this element is 0, and the height of this element is 1. So in this case, roots are equal. The ranks of the corresponding roots are equal. To merge these two trees, we do the following. We just hang the left tree under the root of the right tree. As you can see, in this case, the height of the resulting tree actually increases. And this is the only case when the union operation increases the height of this tree. So in this case, initially, the longest path contained just one edge. In this case, we got a path that contains 2 edges. So we need to update this rank. And this is done in the last check. So if initially the ranks of our 2 trees that are going to be merged are equal, we hang one of them under the root of the other one and increase the rank of the resulting tree by 1. Let's consider a small example. In this case, we have 6 elements. Let's call make set for each of these elements. This fills our data structure as follows. So currently, each element is its own parent, right? So its current set is just a singleton set. Also, the height of each subtree in our data structure is currently equal to 0. Now let's call union of 2 and 4. In this case, the rank of the subtree rooted at 2 is equal to 0. The height of the subtree rooted at 4 is equal to 0. So it doesn't mean which one to hang under the root of the other one. So let's hang 2 under 4. This changes the data structure as follows. Now the parent of 2 is 4, and the rank of the subtree rooted at 4 is equal to 1. Okay, now let's call union of 5 and 2. In this case, the height of the tree that contains the element number 2 is equal to 1, right? While the height of the tree that contains element number 5 is equal to 0. So in this case, we are going to hang 5 under 4. We do this as follows. So this changes the data structure only. This changes only this cell. So now 4 is the parent of 5, and it doesn't change any rank of in our subtree, in our forest. Okay, now let's call union of 3 and 1. This is done as follows. Now 1 has rank 1, and now the parent of 3 is equal to 1. Okay, now let's call union of 2 and 3, and again in this case 2 lies in a set in the tree whose root is 4, and currently the rank of 4 is equal to 1. Also 3 lies in a set whose root is 1, and currently rank of 1 is equal to 1. Which means that after merging these two trees, we will get a tree of height 2. So we do this as follows. Now 1 is the root of the resulting tree, and its rank is equal to 2. Finally, we call union of 2 and 6, and this will just attach 6 to 1 as follows. In our current implementation, we maintain the following important invariant. At any point of time, and for any node I, rank of I is equal to the height of the subtree rooted at this node I. Right? We will use this invariant to prove the following lemma. The height of any tree in our forest is at most binary logarithm of n. This will immediately imply that the running time of all operations with our data structure is at most logarithmic. Right? To prove this lemma, we will prove another lemma shown here on the slide. We're going to prove that if we have a tree in our forest whose height is k, then this tree contains at least 2 to the k nodes. This will imply the first lemma as follows. Assume that some tree has height at strictly greater than binary logarithm of n. Using the second lemma, it will be possible to show then that this tree contains more than n nodes, right? Which would lead to a contradiction with the fact that we only have n objects in our data structure. Here we're going to prove the second lemma by induction on k. Recall that we prove that any tree of height k in our forest contains at least 2 to the k nodes. We're going to prove this by induction on k. When k is equal to 0, this means that we have a tree just of height 0, which means that it contains just one node. So in this case, the statement clearly holds. Now, to prove the induction step, let's recall that the only way to get a tree of height k is to merge two trees whose height is equal to k minus 1. I mean to merge both trees such that the height of the first tree is equal to k minus 1 and the height of the second tree is equal to k minus 1. By the induction hypothesis, both of these two trees contain at least 2 to the k minus 1 nodes, which means that our resulting tree contains at least 2 to the k minus 1 plus 2 to the k minus 1 nodes, which is exactly equal to 2 to the k, right? Which means that the lemma is proved. To conclude, the running time of both union and find operations in our current implementation is at most logarithmic. Why so? Well, just because we keep our trees shallow. So the height of any tree in our forest is at most logarithmic. This immediately implies that the running time of any find operation is also big O of logarithm of n. Recall also that the union operation consists of two calls to the find operation and also a few constant time operations, which means also that the running time of union is also big O of log n. In the next video, we will see another beautiful heuristic, which will just decrease the running time of both these operations to nearly a constant.